What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 4, Chapter Review. Let's do it. Question 1, determine whether the algebraic equation is linear. So in a case like this, the first thing I want to look for is, are there any exponents? There are not any exponents. So this definitely is going to be a linear equation. Likewise, if we simplify a little bit by isolating the y, right, I'm going to subtract 2x from both sides first, so negative 2x plus 7, and then I divide by 3. We get y equals negative 2/3 x plus 7 divided by 3 as well, which is 7/3. Now this is definitive because now it's in slope-intercept form. I mean, this is in standard form, by the way, for a linear equation, but this is also in slope-intercept form if you're trying to grapple with exactly what this line would look like. There, now you can see the slope of negative 2/3 and a y-intercept of 7/3. So this is definitely linear. Boom. Determine whether the function is increasing or decreasing. So first of all, what do those two terms mean? Increasing means it has a positive slope throughout. Decreasing means it has a negative slope throughout. So this is a linear equation. How do we tell whether it has a positive or negative slope? Right here, the value multiplying the x. So since it's 7, it has a slope of positive 7, which means this is increasing. Boom, done. Given each set of information, find a linear equation that satisfies the given conditions if possible. Passes through 7, 5, 3, 17. So the first thing I'm going to do with this is I'm going to stack the coordinates right on top of each other and calculate the slope. The reason why I like to stack is because then it reminds me we're just going to subtract down for both of these x and y values. And I do the difference of the y values on top, 5 minus 17, rise, okay, over the difference of the x values, run. And notice I'm subtracting down in both instances. So 5 minus 17 is negative 12, 7 minus 3 is positive 4. That becomes a slope of negative 3. Now that I know my slope, now I can use point slope to come up with the linear equation. So check this out. I'm going to arbitrarily select this coordinate, and I'm going to say y minus the y value, which is 5, equals the slope negative 3 times x minus that corresponding x value, which is 7. Then we're going to distribute, and we have y minus 5 equals negative 3x plus 21. Last but not least, I'm going to add 5 to both sides like so, and I get y equals negative 3x plus 26, and there's the linear equation. Boom. Find the slope of the line shown in the graph. So to find an appropriate slope, we need to find two appropriate points where we can measure the slope easily. And I always want to choose points that go through those nice crosshairs on the graph. So I see a nice point right here, and I see another nice, easily identifiable point here. And now all I have to do is look at the rise over the run, going from one point to the next. So it has a rise, meaning it goes up by 3, and a run, meaning it goes across to the right by positive 1. So my slope is going to be rise over run, 3 over 1, which is a slope of 3. Boom, done. Write an equation in slope-intercept form for the line shown. So slope-intercept form, I need to identify the slope and the y-intercept. So I can see that the slope, by choosing these 2 points here, is going up 2 and over 1, both of those positive values. So it's a slope of 2 over 1, which is a slope of 2. And then the y-intercept is where it hits the y-axis, which is at negative 2, which means my equation for the line in slope-intercept form is y equals the slope, 2, times x, plus that y-intercept value of negative 2, or minus 2. There's your equation. Boom, done. Does the following table represent a linear function? If so, find the linear equation that models the data. So what I'm going to do is I'm looking first at how much the y values, or excuse me, the x values are changing in each of these cases. So it goes up by 2, goes up by 4, then goes up by 14. Now, the fact that it changes isn't definitive of anything, whether it's linear or non-linear. We have to look at how the y values change, or the function values change relative to the x values. So this one is going down by 4 here, it's going down by 6 here, and here it's going down by 28, right? Negative 28. Now we look at the ratios of each of these changes. So it's function value or y value over x. So it's negative 4 over 2. This one would be negative 6 over 4. And this would be negative 28 over 14. And if all of these are exactly the same, then we have a linear function. But they're not, right? This equals negative 2. So does this. That equals a change of negative 2. This equals a change of negative 3/2. So a linear function, the rate of change, aka the slope, must be consistent throughout, is not here, which means this does not represent a linear function. Boom, done. So for this, we're determining whether these two lines are parallel, perpendicular, or neither. So I want to do that by putting these both into slope-intercept form. Then I can look at the slope, the y-intercept, etc. So I'm going to isolate y in the top equation first. So I've got negative 6y, then I'm subtracting 2x from the other side, plus 12. And then I'm going to divide everything by negative 6. Negative 2 over negative 6 is positive 1/3. 12 divided by negative 6 is negative 2. So there it is, slope of 1/3, y-intercept of negative 2. Now let's do this one. So we're going to add x to both sides. So I got 3y equals x plus 1. And then I'm going to divide both sides by 3. Y equals, and again, there's an invisible 1 in front of that x. So that's 1/3 x plus 1 divided by 3, which is 1/3. So when we look at these two equations, they have a different y-intercept, but they have the same slope, a slope of 1/3. If two lines have the same slope, different y-intercept, that means they are parallel. Boom, done. So here we're going to find the x and y intercepts of this equation. Now, when we have our x and y intercepts, it's important to note that, for example, for the x-intercept, y is going to be 0. For the y-intercept, x is going to be 0. So this is my x-intercept. This is my y-intercept. And when we know that, it becomes a little bit easier because I can just plug 0 in, right, for y and see what we get for x. So that goes away. 9 times 0 is 0. So I have 7x equals negative 63. Divided by 7, we get x equals negative 9. So that's my x-intercept. Likewise, for the y-intercept, I'm going to plug 0 in for x, right, because that's the y value when x is 0. So that goes away. And then we have 9y equals negative 63. Divide both sides by 9. Y equals negative 7. So my y-intercept is 0, negative 7. There's your answers. Boom, done. So for this exercise, we're going to calculate the slope of both of the lines and then see if the two lines are parallel, perpendicular, or neither. So again, for line 1, I'm going to stack the coordinates like so. Then I'm going to subtract down. First, I'm going to take the difference of the y values over the difference of the x values, 5 minus 10. This gives me 11 minus 1 is 10 over 5 minus 10 is negative 5. So this gives me a slope of negative 2. And then for line 2, again, we're going to stack those coordinates. Likewise, we're going to subtract down. So we got 3 minus 11 on top, negative 1 minus negative 5 on the bottom. 3 minus 11 is negative 8. Negative 1 minus negative 5, that's like plus 5, is positive 4. This also equals negative 2. So these two lines actually have the same slope. And so we're going to assume that they're not the same lines. And we can actually see that because this has 511, this is negative 511, right? So they're not the same line, which means if they have the same slope, they must be parallel. Boom, done. Write an equation for a line perpendicular to this and passing through the point 520. So first of all, if it's perpendicular, the slope is going to be the opposite reciprocal of 5. Reciprocal of 5 is 1/5. Opposite means we negate it. So we got our slope. And then we got this point that it's passing through. So I'm going to use point slope. So I got y minus the y value 20 equals that slope of negative 1/5 times x minus that corresponding x value of 5. And then what we're going to do is we're just going to isolate y to put it in slope-intercept form. So we're going to distribute. We got y minus 20 equals negative 1/5 x. Negative 1/5 times negative 5 is positive 1. And then I'm going to add 20 to both sides like so. And we got y equals negative 1/5 x plus 21. Or if you want to put this in decimal format like the back of the book, y equals negative 0.2x plus 21. Both are correct. Boom, done. So for this one, it says sketch a graph of the linear function, and we have two things. We have the slope here, and we have the y-intercept here. So using those two pieces of information, we're going to graph it out. Here's my y-intercept. We plot that first at negative 5 on the y-axis. And then a slope of 2 means really 2 over 1, right? So it's a rise of 2, a run of 1. So we go up 2 over 1, up 2 over 1. And now we're going to connect the dots like so. And there's your final answer. Boom, done. A car rental company offers two plans for renting a car. So for A, it's $25 per day plus 10 cents per mile, where X is the number of miles. We don't know how many miles we're driving. And then for plan B, it's $50 a day plus unlimited miles, right? We don't have a cent per mile or anything like that. So these are the two rates for one day. So then it says, how many miles would we need to drive for plan B to save you money in one day? So first, let's figure out when these two are going to be exactly equal. So I'm going to set them equal to each other, and then we're going to solve for x. So I'm going to subtract 25 from both sides. I got 0.1 x equals 25. Divide both sides by 0.1. That's like multiplying by 10. That's 250 miles. So at exactly 250 miles, the two plans, you're spending the exact same amount. So if you drive for more than 250 miles, that's when plan B saves you money, because that's when plan A will get more expensive. So more than 250 miles, boom, done. The town's population increases at a constant rate. In 2010, the population was 55,000. By 2012, it had increased to 76,000. If this trend continues, predict in 2016. So the easiest way to do this is we're going to take that first early value of 2010. I'm going to consider that to be times 0, okay? So then my x values are going to be the amount of time or amount of years since 2010. 2 would represent 2012, 4 would represent 2014, etc. So I got a value of 0, 55,000, and then I've also got a value of 2 years later, 2, at 76,000. Now I can create a linear equation and then use that to predict the population in 2016. So first, let's calculate the slope by subtracting down. So we got 55,000 minus 76,000 over 0 minus 2. So then 55,000 minus 76,000 is negative 21,000 over negative 2, which that reduces to positive 10,500. And that's my slope. So now I've got an equation of y equals 10,500x plus that y-intercept of 55,000, right? And then we got a nice equation. Now to solve this, I plug 6 in for x, because 6 represents 2016, aka 6 years from 2010. So 6 times 10,500 is 63,000 plus 55,000, which gives us an answer of 118,000. So that's the population in 2016, at least that's predicted. Boom, done. All right, here we're meant to find the linear function y, where y depends on x. And the way we're going to do that is we're going to look at two nice, easily identifiable points. Then we're going to calculate the slope, use point, slope, etc. So here I've got a point at 5, 10,000. And here we got a point at 25, 4,000. And then what I'm going to do is I'm going to stack the coordinates, and then we're going to subtract down to calculate the slope. So 10,000 minus 4,000 on top over 5 minus 25 on the bottom. So then we got positive 6,000 over negative 20, which simplifies to negative 300 for the slope. Now we're going to arbitrarily choose 5, 10,000 as our coordinate, and we're going to plug into point slopes. Let's do it up here. We don't have a ton of room, but I'll say y minus that corresponding y value of 10,000 equals a slope of negative 300 times x minus 5. And then as we distribute, we get y minus 10,000 equals negative 300x, and then 300 times 5, or negative 300 times negative 5, is positive 1,500. Last but not least, we're going to add 10,000 to both sides, and we get y equals negative 300x, and then 10,000 plus 1,500 is 11,500. There is your final linear equation. Boom, done. For the following exercise, consider this scenario. In 2004, school population was 1,700. By 2012, it had grown to 2,500. So we're going to turn these both into coordinates, with 2004 serving as year 0. So I'm going to say 0, 1,700. And I'm going to say for this one, that would be 8 years after. So we could call that 8, 2,500. So we got those in coordinate format. Now it says, how much did it grow between the years 2004 and 2012? So it went from 1,700 to 2,500, so that went up by 800. That's our answer to part A. What is the average population growth per year? That's our slope. So again, we can just finish this calculation. 1,700 minus 2,500, again, we're subtracting down over 0 minus 8. So that gives us negative 800 over negative 8, which simplifies to 100. That's our slope, and that's the average population growth per year. Last but not least, we need to find the equation of the population t years after 2004. So if we say p, population, is a function of t, it would equal the slope, which is 100, times t, plus my y-intercept, which we have designated as 1,700. And there is the answer. Boom, done. For the following exercise, consider the scenario. In 2000, the moose population was measured to be 6,500, and by 2010, it was 12,500. And assume this happens linearly. What does the model predict the moose population to be in 2020? So question 30 actually asks us to create the model. So we'll do that here as well, and then we'll use the model after the fact. So we got these nice two data points. In the year 2000, which I'm going to place as times 0, right? So this will be the amount of years from 2000. It has a population of 6,500, and then 10 years later, when X would be 10, it would have a population of 12,500. Now we're going to subtract down and calculate the slope, 6,500 minus 12,500, difference of the Y's over the difference of the X's, top minus bottom, 0 minus 10. That becomes negative 6,000 over negative 10, which is a slope of positive 600. So the model then is P of T equals slope of 600 times t, and again, t is the years from 2000, plus my y-intercept, which is 6,500. And then to get our answer, we want to know what's the population in 2020, aka 20 years from 2000. So that's what we'd plug in for t. So 20 times 600 is 12,000 plus 6,500, which means the model predicts a population of 18,500. Boom, done. For the following exercise, consider the scenario. The median home value in Prima Central and East Valley are shown in Table 1 from 1970 to 2010. If these trends were to continue, what would be the median home price in Pima Central, which is this area? So we're assuming it's changing linearly, so we can make a linear function for Pima Central, and we're going to calculate the slope. Now look at this. These are actually stacked perfectly for us, and I'll just make year 1970 year 0 and year 2010 the amount of years from 1970, which would be 40. So to calculate the slope, we're going to subtract down. So it's 32,000 minus 85,000 over 0 minus 40, right? 0 minus 40. And that gives us negative 53,000 over negative 40. Cancel out a 0. And then it's 5,300 divided by 4. And that gives us a value of 1325 for the slope. So now we can get a linear equation for this, which would be y equals my slope times x plus my y-intercept of 32,000. And now if we want to make a prediction for 2015, that's 45 years from 1970, which means we'll plug 45 in for x. So 45 times 1325 gives us 5,9,625 plus 32,000, which gives a final answer of 91,625 for the predicted median home value in 2015 for Pima Central. Boom, done. So here we're going to draw a scatter plot for these data points, and then we're going to answer this question of interpolation versus extrapolation for 15,000. So now we got a little graph up here. Sorry, it's kind of in the middle. We just don't have a lot of room. So now we're gonna plot out these points. So now we have 1990 occurring at 5,600, which is right here. Then we have 1995 occurring at 5,950, just under this guy, under the 6,000. Then we have 2000 occurring at 6,300, which would be right here. Then we have 2005 occurring at 6,600 right there. And then last but not least, we have 2010 occurring at 6,900 right there. So that looks pretty linear to me. Then it said if we want to know when the population would reach 15,000, would it involve interpolation or extrapolation? Well, 15,000 is outside of the range of these population values, right? We're beyond 15,000. So we're going outside of the data set versus if it said like, hey, when is the population going to reach 6,500? That's within the data set, right? We have values below and above 6,500. So this would be extrapolation, boom, done. So for this question, we're just trying to thread the needle, as I like to say. We're trying to draw a line that goes right kind of through the center of all of these guys. And it's approximation, but we're really threading the needle here. And that looks like a nice approximation for a line of best fit. Kind of goes through the center of all the data points. That's how you do it. Done. So this table provides the percent of unemployed in a city of 25 years or older, right? So this would be like 6.5%, 7% in these various years. And it looks like it's increasing. And I think the assumption is that it's increasing linearly. So it says, in what year will the percentage exceed 12%? So what we're going to do is I'm going to take two values and we're going to kind of assume that this is linear. And we're going to say 2000 to 2002, 6.5 to 7.0. That's a difference of 2. This is a difference of 0.5. So we're going to calculate a slope, and it looks like it's changing 0.5, the difference of the y's, over 2, the difference of the x's of time. And 0.5 over 2 is 1/4. So this is going to be the slope of the line. And we're going to set 2,000 as times 0. So this value is our y-intercept. So we can make a nice equation. Y, which represents the percent, equals 1/4 x, which is the year, plus 6.5. So assuming this linear model is legitimate, now what we're going to do is we're going to say, when are we going to exceed 12%? And that's the y value. So we're going to plug and chug, and then we're going to solve for x. So first I'm going to subtract 6.5 from both sides like so. 12 minus 6.5 is 5.5 equals 1/4 x. Then to isolate, we multiply both sides by the reciprocal of 1/4, which is 4. That becomes 22. So that's 22 years after 2000, which means it will exceed 12% in the year 2022. Boom, done. So for this question, we're going to use the linear regression calculator on Desmos to do this calculation and then create and find the correlation coefficient, all that good stuff. So when you plug in these points, these are the values that you get for R, the correlation coefficient, and then the slope and the y-intercept. So let's get those values and let's write it all out. So we got a correlation coefficient of negative 0.974, and my slope would be negative 1.294, and that's times x plus that y-intercept of 49.41, and then we'll round up 0.412. That's the answer. Boom, done. For the following exercise, consider the population increasing steadily over a 10-year span, and these ordered pairs show the population and the year, right? That's the year second, population first. And then it says predict when the population will hit 12,000. So what we're going to do is we're going to create a linear equation. So I'm going to use 2 arbitrary coordinates. I'm going to use the first 2. And then we're going to subtract down to calculate the slope. So 2,000 minus 2,001 is negative 1. 3,600 minus 4,000 is negative 400. So there's my slope, is 1/400. So then now we can use that slope of 1/400 in point slope to come up with a model. So it'd be y minus, let's take that value of 2,000, equals 1/400, that's the slope, times x minus, again, this is point slope, x minus that corresponding x value of 3,600. We're going to distribute. Y minus 2,000 equals 1/400x. And then that's 1/400th times negative 3,600. That's 3,600 divided by 400, or 36 divided by 4. And that's 9, or negative 9. Last but not least, we'll add 2,000 to the other side. Y equals 1/400x plus 2,000 minus 9 is 1991. So since the population is the x value, I'm going to plug in 12,000 in for x, and then we're going to solve. So we get y equals 1/400 times 12,000, which ends up being 30, plus 1991 gives us an answer of 2021 for the predicted year. Boom, done. For 45, it says, according to the model, what is the population in 2014? So I'm going to put the model back up that we got in question 43. And now we're going to plug in 2014. And again, the year goes in for y. So we got 2014 equals all of this. Then we're going to subtract 1991 from both sides. That is 23. And 2014 minus 1991 is 23. And then 23 equals 1/400x. Last but not least, multiply both sides by 400. And then 400 times 23 is 9,200. So the population in 2014 is 9,200. Boom, done. I hope you guys enjoyed this video. And if you did, please click that like button. And if you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.